Okay, hi. So we will start our discussion on discrete time Fourier transform or the Dtft. Okay, so far we have seen Fourier series. We saw the Fourier series for the continuous continuous time signals, as well as for discrete time signals, and we also then we saw the Fourier transform for continuous time signals, right? And we said that we would like to analyze all signals using the uniform domain of Fourier transform, because that can accommodate both periodic as well as aperiodic signals. But the continuous time Fourier transform, which we saw in the previous topic, is actually not practical, because the time there is a continuous time. Okay, to represent it using a digital computer, we need discrete time. Okay, we cannot represent continuous quantities. So since we have to discretize it, and practical signals which we are going to use are going to be discrete time signals, we will extend the Fourier transform to analyze discrete time signals, and hence we get the Dtft, or the discrete time Fourier transform. Okay, so we want to do signal analysis in the domain of Fourier transform, but by using discrete time signals. So hence we have the discrete time Fourier transform. Okay. Okay, one more thing which we saw earlier was the Fourier transform representation for discrete time signals is a finite series, because see, once you start representing signals with complex exponentials, discrete time complex exponentials, discrete time complex exponentials with separated by frequency of 2 pi are the same, right? So as a result of this, the number of harmonically related complex exponentials for in the discrete time domain is limited. Okay, so if there is a periodic signal with period n, there are only n harmonically related complex exponentials, discrete time. Because of that, the Fourier series representation for discrete time signals is a finite series. That series has length n, which is equal to the period of the signal you are representing using the Fourier series. So we will now see how the Dtft is constructed. For example, so we will follow the analogy exactly same as what we did in the continuous time case. So imagine that there is a signal x of n which exists for this duration. Okay, minus n1 to some plus n2. So this is xn, and then we will construct a periodic version of this. We construct a periodic version which we call x tilde n, right? And this period is what is n. Okay, so this signal is repeated periodically with a period of, this is capital N. So this part and this part are from here, and then this thing repeats, and this period is n. Okay, so this is essentially a discrete time periodic signal with period n. And of course, because of that, since it is a periodic signal, it has a Fourier series representation. So I can write by using the synthesis formula, x tilde of n, that is my periodic signal, discrete time signal. X tilde of n will be represented by using a Fourier series, where ak are the Fourier series coefficients. E raised to jk 2 pi by n is the fundamental frequency. N is this period n, this is n, that same as this n, and since there are only n harmonically related complex exponentials, this summation for the Fourier series is over n, right? And the AKs are given by the analysis formula, okay, in terms of x hat of x tilde of n, and this is also done over a one period. Okay, so this summation here goes over any interval of n. So we can also now, because this over one period is same as this over minus infinity to plus infinity, I just rewrite this one here with x. I replace the x tilde of n with x of n and change the summation to minus infinity to infinity, because I'll get the same thing. And then we define a new function x of omega, which we define as x of n e raised to minus j omega n, when n goes from minus infinity to infinity. Okay, so this expression must be familiar to you. So this is essentially a continuous function of omega. This x of omega is a continuous function of omega, and then from looking at this expression, by looking at this expression, we can see that ak, the Fourier series coefficients, are nothing but samples of this x of omega taken at k omega naught, where omega naught is 2 pi by n. Okay, so this is my ak, and as my n increases, that is, as my period becomes larger and larger, this signal will finally become this in the limiting sense, and the period becomes infinite. So as n increases, your 2 pi by n, which is your omega naught, that will decrease, right? So basically, essentially, if you remember it from the continuous time case, if this is my x of omega, this is my x of omega, as n increases, this samples will become smaller and smaller. The values you are taking of x of omega become more and more dense, and of course x of omega is periodic with period 2 pi, because for discrete time exponentials, any frequency separated by 2 pi are the same, and then by some rearranging some expressions, since 1 by n is omega naught by 2 pi, we get an expression for x tilde of n, which is equal to 2 pi x of the k goes to over summation of n, x of k omega naught e raised to j k omega naught omega naught, right? So I just replace, I just change the variables and just rewrite this expression, and essentially what we are getting is, now we are basically writing your x tilde of n, your periodic signal, in terms of samples of x of k, in terms of samples of x of omega. Okay, and as your omega naught becomes smaller and smaller, as n becomes larger and larger, this expression now becomes the omega naught will now become a d omega, because the width is infinitesimally small. K omega naught becomes omega, and this expression, this summation over n, is essentially n you are summing over intervals of omega naught n times, and that will give me n into 2 pi by n, which will give me a interval of the summation. In this case, this one becomes this expression, this becomes now 2 pi, because essentially what you are doing here is, you are taking n sums of each of the width omega naught, right? So that is nothing but n into 2 pi by n. Omega naught is 2 pi by n, so n into 2 pi by n. So this value here is from any interval of value 2 pi. So by doing this, we get the Dtft pair, which is your x of n and your x of omega. The synthesis equation is what we just saw here. You are representing x of n. So this is over any interval of 2 pi, x of omega e raised to j omega n d omega. Omega still here is a continuous variable, please remember that. And this is the analysis formulation, where you need to get an expression for x of omega. X of omega is what we had defined here earlier, right? X of omega is what we had defined this as the earlier. So this is my x of omega. So if you see, if you compare it with the continuous time Fourier transform, it is exactly parallel to that, except that here the analysis is done over discrete time, and your x of omega is now, because we are representing the spectrum of using discrete time signals, your x of omega now becomes periodic, because any discrete time exponential separated by 2 pi is the same, right? due to that. So how is it different from the CTFT? It is different from CTFT because x of omega is periodic for DTFT. How is the DTFT different from CTFT? X of omega is periodic, whereas in the CTFT x of omega is not periodic. X of omega is a variable which is not periodic here, but here, because of the property of discrete time exponentials, or because of discrete time signals, here x of omega is periodic. And of course this synthesis equation is now, this synthesis equation is done over a finite interval of 2 pi. So that will come into play when we discuss convergence. So some examples from the textbook. Look at example 5.1. X of n is a n u n, which is a decaying exponential causal if a is greater than 0. So if you apply the Dtft formulation, you get an expression for x of omega by substituting x of n in this equation, and essentially you get 1 by a e raised to minus j omega. So this is a complex number, right? This is a complex function, and this is plotted here for various two values of a. When a is greater than 0, your x of omega looks like this. When a is greater than 0, and when a is less than 0, the x of omega looks like this. So the main thing to remember here is that, see, if you consider minus pi to pi, okay, so this is a interval of 2 pi. Now if this is 0, at 2 pi this will start to repeat, because this will periodically repeat with period 2 pi. This is the spectrum here is periodic. Okay, please, this is a crucial point here. The spectrum is periodic because the signal has a discrete time. The spectrum now becomes periodic, and this is the magnitude, and this is the phase. The phase will also be periodic because omega is a periodic function. So this is the case when a is less than 0. So this is the magnitude and this is the phase. So you can see that when a is greater than 0, this is essentially a low pass filter because it passes values around 0, and when a is less than 0, this is essentially a high pass filter because the frequencies around 0 are attenuated. Another expression, another example from the book 5.2. This equation this signal we had seen earlier also in the continuous time case. X of n is a mod n, where a is less than 1. It is a decaying signal. So the signal in time looks like this. So it's, if you substitute into the Fourier transform Dtft, the Dtft looks like in this particular way. So again, it is periodic with period of 2 pi. You can see that it is like a low pass filter. Another example, example 5.3, which is the well known square pulse, minus n1 to plus n1. This we saw earlier that this signal in the continuous type transforms to a sink. So here also this transforms to a sink. Something like a sink, because this is not really a sink, because sink in general is not a periodic signal, but because here in this case our omega is periodic, we will get a periodic version of the sink function. Okay, so the expression is this one, and of course this signal is real and even. So you'll see later from the Fourier transform, the Dtft properties, that if the signal is real and even, the Fourier transform is going to be real. Convergence issues, we will not touch upon them very much in detail, but if you look at this expression, the analysis formulation here, it goes from minus infinity to plus infinity. So we have to worry about convergence. So how do you, for a given x of omega, x of n, how are you sure that x of omega will exist when you are doing an infinite summation? So two conditions are there. If x of n is absolutely summable, then if it is absolutely summable, then x of omega will exist and this will converge uniformly. and if x of n is square summable, then also the x of omega will exist, but in that case the convergence will happen in the mean. With respect to the synthesis equation is easier because it is the summation is over a finite period of 2 pi. Okay, we don't need to integrate it over minus infinity to plus infinity. So this is over a finite period of 2 pi. So so for example, if you see so if you have an approximation, a partial sum, which I call x hat of n, which you obtain by applying the inverse Dtft to x of omega. So x of omega is the Dtft of some x of n, and if you apply the inverse Dtft over minus omega this minus capital omega to some plus capital omega, we need to do it only between a thing of 2 pi. Okay, so we are doing something in middle of that, minus omega and plus omega, and this x hat of n will be equal to x of n when this omega is equal to pi. So that means if you do it from minus pi to pi, your x hat of n will be exactly equal to x of n. Okay. You can see a couple of more examples from the textbook. Now the Dtft which we saw so far was okay, just one aside, Dtft we saw now was, we saw some examples of the Dtft. So this is discrete time and this is the Dtft, but still this also is not practical. Dtft, although the time is discrete and we can represent it digitally in a computer, we still cannot use Dtft because the frequency variable omega is still continuous. Okay, this is still a continuous quantity, so we cannot represent continuous quantities. So the discretization here has happened only in time. So to use it in practice in a computer or in an algorithm, you basically need discrete time as well as frequency. So this also has to be discrete. That is, for that you need to use what is the known as the discrete Fourier transform, or the DFT. Okay, so we will not cover DFT in this course, but essentially DFT is essentially your continuous the spectrum, the continuous spectrum obtained in Dtft. If you sample that and take samples of that spectrum, very similar to your, actually it's very similar to your discrete time Fourier series, then you can represent it using a computer. So in practice we don't use CTFT, we don't use DTFT, we use only the DFT, discrete time, for the discrete Fourier transform. So now this, how do you do the Dtft for periodic signal? So far we have seen signals which are not periodic. So to extend the Dtft to periodic signals, similar to what we did in the continuous time Fourier transform, we had to extend it using to incorporate periodic signals into the Fourier transform, we had to use delta functions in the Fourier transform. So if we also so the Dtft also we will do the same case. To extend it to analyze signals which are periodic, we have to start using delta functions in the frequency domain. So for this, consider x of n, which is a discrete time exponential, complex exponential, e raised to j omega naught n. Okay, so in the continuous time Fourier transform, we saw that this signal, if this were t, for example, e raised to j omega t, this would have had a Fourier transform, which this is 0. No, this would have had a Fourier transform. If this is 0, you had you had a delta function at omega naught. So this was the Fourier transform for e raised to j omega t. So now if you want to represent this using Dtft, you want to have a discrete time Fourier transform for this, the main thing is that Dtft has to be periodic. So that we can do by construction. So actually the x of omega will now look like del of omega minus omega naught. So you have a delta function located at omega naught, and you explicitly add a minus 2 pi L, and L goes from minus infinity to infinity, and you have this 2 pi because you need to cancel out the 2 pi when you take the inverse Fourier transform. So a scaled impulse which periodically repeats. Okay, so the for this e raised to j omega naught n, the Dtft looks like this. Okay, so at various omega plus 2 pi, omega plus 4 pi, you get an impulse stream. Essentially it is an impulse stream in the omega domain. Now if you want to extend this to, let's say, a periodic sequence with which has a Fourier series, this one, so this is your x of n is a discrete time, the periodic discrete time signal, and so it has a Fourier series, and this is the Fourier series. Of course the Fourier series is going to be finite, because there are only, if it has a period n, there will only be n harmonically related complex exponentials. So this is my x of n, which I represent using a Fourier series. Its Fourier transform can be shown to be this one, x of omega is 2 pi ak are the Fourier series coefficients, del of omega minus 2 pi k by n. Okay, essentially, so this comes as a result of if your e raised to j omega n has this as the Fourier transform, a linear combination of e raised to j omega naught n's will have Fourier transform which is also a linear combination. So it comes from that. So so if you analyze this expression for so if you look at your x of n and you are going to represent it using this Fourier series, let us take each term here and compute its Dtft. Okay, so there are n such terms here. So for k is equal to 0, k is equal to 1, k is equal to n minus 1, these are the n terms which comprise its Fourier series coefficients. So by the analogy with this example, when k is equal to 0, there will be so this is essentially this term is going to be 0, and so essentially your Fourier transform here will be the omega naught here is essentially 0, right? When k is equal to 0, this 2 pi by n is your omega naught. So when k is equal to 0, this is e raised to 0 n. E raised to 0 n essentially means your omega naught here is 0, e raised to 0 n, right? This omega naught, so this omega naught is going to be 0, so you will get a delta function at 0, and since it is periodic, you will actually get one more delta function at 2 pi. This has a period of 2 pi. Okay, so this is essentially also because this Fourier series coefficients are also periodic with a period of n. So if this is 2 pi a naught, this is okay. Then if you consider the second term, this will be ak e raised to j omega naught n. This is, so here in this case you will get an impulse located at omega naught, which is your 2 pi by n, and that impulse that will be scaled by 2 pi ak, because that is how we have got it here, right? 2 pi multiplied by whatever is the Fourier series coefficients there. And similarly you do it for all the terms, k is equal to 0, 1 to n, and if you put them all together, essentially you will get, this will be the Fourier transform of this particular signal which is represented by the Fourier series. Fine, so this is essentially an impulse stream. Since the Fourier series coefficients are automatically repeating, we don't have to explicitly add the repeating term here. That is taken care of by the impulse stream because it repeats. Another example, example 5.5, xn is cos omega naught n with omega equal to, let's say, 2 pi by 5. This is given to be 2 pi by 5. So here the Fourier transform, here you can directly apply this case here. You can directly apply this. Where is this? Yeah, you can directly apply this case because e raised to j omega naught n. You can express this as the Euler formula, and you get the Fourier the Dtft to be like this, because you will have one at omega minus 2 pi by 5, the other one you will have this one at omega plus 2 pi by 5, and it repeats with period of 2 pi. This is a discrete, this is example 5.6, discrete time impulse train. Impulse train looks like this, del of n minus kn with a period of n. So from the previous example we saw that, from previous discussion we saw that ak, if you represent it using a Fourier series, this is a periodic function, right? So if you have a Fourier series, and the Fourier series coefficients we saw earlier was 1 by n. So we can apply this one here. So essentially x of omega will now be 2 pi by n del of omega minus 2 pi by n k. This 2 pi by n comes because of it is this 2 pi my ak here is 1 by n, so it is 2 pi by n. So please have a look at the initial portions of Dtft. We will cover the rest of it in the subsequent lectures.